Hi, in this video we are going to start looking at signal conditioning for piezoelectric sensors. If you remember in the previous videos we talked about the electrical model of piezoelectric sensors, and we basically talked about the fact that piezoelectric sensors can be represented in two different ways. On the one hand, we can represent piezoelectric sensors as a voltage source, and the capacitor and the leakage resistance of the piezoelectric crystal appear like this. On the other hand, you can think of piezoelectric crystals as a charge source or a current source, because current is just a differential of charge or change of charge, right? So a charge source with the capacitance and the leakage resistance appearing like this. Okay, so let's think about how we can use and amplify the voltages of the charge that comes on the piezoelectric sensor. And the first method that we will use is basically the voltage amplification. Okay, so what we are saying here is, so this is our piezoelectric crystal, right? You have a voltage, the capacitance of the crystal, and the leakage resistance. And one way to amplify this voltage would be to just give it to a non-inverting amplifier, right? So when you give it to a non-inverting amplifier, whatever voltage appears here is going to be amplified. Now, of course, the voltage that appears at this point is not going to be equal to Vs. It's going to be slightly different because it's going to divide between Cs and Rs. But well, whatever this voltage is, that can be amplified. Now, one of the things that you need to notice is there is a requirement that we have a non-inverting amplifier here. We cannot have an inverting amplifier here, right? Why not? I think I'll leave the answer to you, but just give you a hint. Think about what the input impedance of the non-inverting amplifier is versus the input impedance of the inverting amplifier. Okay? Okay. So that's one amplification strategy that we can use as shown here. Now, what are the problems with this strategy? One of the problems is the fact that there would be some leakage capacitance and leakage resistance in the cable that connects the piezoelectric crystal to the amplifier, right? So you will have a cable capacitance and a cable resistance when you attach the crystal to the amplifier, and you have to account for it. Okay, so let's put in these two quantities, and now let's try to get V output. Okay, so how are we going to get V output? To get V output, we know that V output is going to be 1 plus R2 over R1 times whatever the voltage is that appears at the non-inverting terminal. Now, what is the voltage at the non-inverting terminal? It is going to be so this impedance here, Rs, Cc, and Rc, we can combine these, and that forms one impedance, and Cs forms the other impedance, and this then becomes just a voltage divider circuit, right, between this Cs and the combination of these three impedances. So let's just try to evaluate that. So as I said, we need to evaluate V plus. And what is V plus going to be? It's going to be Rs in parallel with the impedance of this capacitance in parallel with Rc. And so that's the impedance of this part. And the total impedance is Cs plus this impedance. So ZCS plus this impedance. Now, if we are able to get V plus, we'll be able to get V naught as well. So let's try to evaluate this parallel combination here. So if we evaluate the parallel combination, it's going to be, let's call Rs parallel Rc as Rp, just the parallel combination of this Rs and Rc, parallel ZCC, and then you can do the mathematics and you get this, okay? Where I'm going to leave this as Rp for now. Now we can substitute this back into this equation and see what we get. So you can do the mathematics. I'll leave you to do the arithmetic. And what you get is something like this. Okay. Now what we want to see is, what does this tell us about the response here? What does this tell us? Okay. So let's plot this response and try to see what information it gives us. So from here, you can see that the gain of this amplifier, when omega is very high, okay, when the frequency becomes very high, is what? So this becomes, this term here becomes much higher than 1, and therefore this 2 cancel, this entire thing becomes 1. So the high frequency gain is CS over CC plus CS, okay, as shown here. And at 0 frequency, you can see that the gain becomes 0. So first of all, this is a high pass characteristic. And of course, we expected that for a piezoelectric crystal. We can see that the cutoff frequency is at this particular frequency, which is given by this quantity here, and the gain is given by here. And you can see that the gain and the cutoff frequency both have this cable capacitance and the cable resistance in the terms, right? If the cable capacitance is much less than the capacitance of the sensor, then you can ignore it, right? You can ignore this, and this gain becomes 1, and the cutoff frequency also becomes independent of the cable capacitance. Excuse me. So that's when the cable capacitance is much less than the sensor capacitance. But that may not be true, because the capacitance of the sensor as such is very small, and then you have the cable capacitance, and therefore the cable capacitance may not be much smaller than the sensor capacitance. Also, remember what we had said before. The problem here is not the cable capacitance per se, but the fact that the cable capacitance would change. Or as you use the sensor in different applications, your cable capacitance would change. And we don't know what the capacitance is. And therefore, the gain and the cutoff frequency would keep changing. So that's one of the problems with this kind of a signal conditioning setup. Okay, of course, some of the ways that we talked about before, like shielding and like reducing the leakage resistance and things of that kind, might help in reducing the cable capacitance.